So thank you so much, Dean Okamura, for your kind invitation and very nice introduction. So I'm very glad to be able to share our recent work with you. And you can see that my background is mainly in computer science, but I have a passion in art. And recently, my PhD student did some work in architecture. So we kind of use some of our own visual language approach to do the floor plan generation. So the work that I'm going to present mainly published in these two papers. So if any of you interested to look at the details, and those are the papers that later on we can also discuss. So I will try to just select a few sort of technical details. So hopefully I have a little bit more time later to share with you some of our generative art projects. Okay, a lot of pictures. Okay. So this is a general outline. So firstly, I will give you an introduction, and then the framework. Actually, we combine the so-called shape grammars and graph grammars. Actually, shape grammars are designed and invented by architect, right? And George Stinney from MIT. He's an architecture professor. And graph grammars is based on our own work. And I will just discuss with you how actually we combine these two grammars, and then we validate the styles of floor plans, and then also generate floor plans with the users specified a few constraints, hopefully more practically usable. Okay, and then overviews of some other projects. I mentioned some information visualization and also generative art. So firstly, introduction, and just a quickly overview the shape grammar. I guess most of you probably are familiar with, so I'm not going to go much details. And basically by George Stinney and James Gibbs, these are just the grammar rules. You can see left graph, right graph, they are just shapes. And based on this rule, you can actually generate all sorts of different shape combinations. So it's very well established, and but the only issue is that it's actually not tractable. And in other words, we cannot validate after the generation. So, and this is a general framework of shape grammar. Basically, design generation is through the initial shapes and plus the shape transformation rules, and then plus execution sequence. Execution sequence actually, so far, they don't exist actually before the real software development, because we have to make it runnable. Okay, so that's based on the interpreter that we call it shape grammar interpreter that we also developed from there. So this is shape grammar rules. Initial shape could be like that, and the rule could be this rectangle, add another rectangle on top, so you can actually generate all sorts of combinations, right? This is pretty easy, and this is by the standard definition. And you can also have three-dimensional shapes and all sorts of combinations. This is useful and has been published around for quite a while. And also, shape grammar applications have been around for some time. You can see paintings, architecture design, and pattern design, industrial designs, and mechanical engineering parts as well. Because basically the same principle we can apply. And this have been around, and you can see George Stinney and his colleagues, they have published quite a few papers in these areas in the past 30 or so years. And this is some of our applications, this is our application, and some other applications, this is kind of a lattice window shape and automatically generate. And but there is a main limitation, as I mentioned earlier. Designs generated by shape grammars are intractable. Intractable, that means you cannot really automatically verify whether the generated designs are correct, are the true kind of a style that you have specified. Okay, basically there is just one way forward. You generate, that's it. You generate all sorts of combinations, but you cannot come back. Say, okay, this generation is from this rule, and actually it does satisfy this grammar. That kind of things, we can do something. So that's how we use the so-called graph grammar. Graph grammar, we do have such a system that I have worked on for the past 20 years, actually quite a long time, on the graph grammar formalism. And it's basically a 2D formalism for specifying various kinds of visual languages with rules. And we call them productions, sometimes just call them rules. And this is just one production example, and the left-hand side is a node, and the right-hand side. Don't worry about the detailed here, and it takes time to explain all these notations, okay? And we don't need to go to that details. And then they're used in computer science for modeling and analyzing syntax and semantics of two-dimensional graph structures. And what do we call visual languages? Basically, when you're programming, you program, say, in Java, nowadays in Python, this is all text, right? Or, you write text statements. But in computer science, there is a sub-area, small area, that is called visual programming languages. That means you draw graphs to make programs, okay? And the graphs can run just like a Java program, textual program to run. But the graph itself can be automatically syntax checked, okay, and compiled to run, okay. So this is the so-called visual programming languages. The underlying theory is called graph grammar, okay. So that's why we try to use this theory to support our floor plan generation. So they're capable of both generating and parsing designs. The second part is what shape grammar is lacking. Parsing designs. The input graph called host graph, we call it host graph, and with given productions. So the parsing itself actually is called L application, and generation itself is called L application, and parsing called R application. Just one is left, the other is right. That's all. So basically, the shape grammars we can apply in both directions. Generation in this direction and parsing in this direction. So parsing itself is to validate. So that's what is missing in shape grammars. Shape grammar can only support one direction, which is for generation. Okay. So that is the reason we introduce graph grammar to do the job. And to summarize this conceptual framework, basically shape grammar consists of a set of initial shapes and transformation rules among the shapes. It's like this: one direction, generating initial design and a floor plan. You convert the initial design to floor plans. And the graph grammar, actually both directions. You start from the empty. This is called empty graph, and deriving, and it's same as generating. Generating and come back, you can verify. That means parsing. You can verify. So that's why this is kind of two-directional, and it's more useful. So the graphs generated by graph grammar are tractable and controllable. Okay, and actually controllable, we also mean that it's executable. We can actually run the generation process itself. Okay. So this is just our previous work to use shape grammars to generate logo design. This is a very simple example. Suppose we have initial shapes just like quarter circles, and we have all sorts of combinations. These are rules, assuming. And then, you see, we actually designed this software called Enhanced Shape Grammar Interpreter. And previously, there is a researcher from Netherlands. He implemented an initial version of shape grammar interpreter. And it's very preliminary and has a lot of limitations. Then we extended his interface and with a lot of powerful features. And now we call it the Enhanced Shape Grammar Interpreter. And it's also open source, although we haven't put into the on the web. And any of you interested, we can actually share with you and to use. You basically can use the interface to construct your rule and then automatically generate all sorts of designs. Okay. And but again, this is based on shape grammars, not graph grammars. So it can only generate. Okay, cannot really do the checking, validation. Okay. So we also applied that for the circulation generation, and this is for shops and museums, right? And you just walk around the floor space, and this is just one small piece of work. We applied the shape grammar to design this. I don't know whether this is meaningful to you. Maybe not meaningful. Circulation design. And then let's look at how we combine the shape grammars with the graph grammars. So basically, we need to convert the shapes to graphs. Okay. So you can see the shape, kind of a square and a rectangle can be, you see, simply represented by a graph by making every vertex as a node here, right? It's quite straightforward, very intuitive. Just make every intersection as a node, as a graph node, and every line as an edge. That's it. Okay, so this kind of a conversion is very easy and automatic. We can use a simple, small program to transform. Okay, and then this is our sort of established foundation. We call it special graph grammar, and that is our own grammar. We actually published quite a few papers in this in the past 20 years. And this is just the notation. Oh, sorry, node, not note. SGG node. And basically, you can see that, we actually can connect to the northeast, the east, and the southeast, and so on. In 8 directions, we can connect with another node or other nodes. Very many other nodes, okay? And so that's why we call it a special graph grammar, that, you can actually specify different directions. And also in computer science, we also had a proof because of the special feature that the parsing speed, actually the complexity, is reduced. That is one of the theoretical contributions that we made, but it's not quite relevant here. So that is just a graph grammar that it was actually enhanced from our previous work called RGG. Don't worry about this. Basically, two types of graph grammars, one built on the other, and one was an enhanced version of the other with a special feature. Okay, so from now on, we simply just mention the SGG, which is a special graph grammar. And so you see that we transforming shapes to SGG graphs, like this one. You see this 2 nodes connected, just like 2 nodes connected east to west. of the second node. And this triangle, it can be just modeled this way. You see, this can be automatically generated easily, okay? And the rules can also be specified this way. If there is a square we want to connect with a new square, we can simply just specify this square. This is the left-hand side of the rule. This is just a square. Right-hand side has two squares. So right-hand side is this one, two squares, okay? And basically in our notation, in SGG notation. And this part is simply just the program, which we call action code. That means when this rule is being passed, and then this program will also be executed. That's why we say the semantics is also related to the parsing, okay? And that means when you do the validation, we can also run a program associated with that rule, okay? So that is powerful. That is actually one of the theoretical contributions we made to the graph grammar. And we make use of it now that in the floor plan generation. So this is our initial attempt to actually validate the Turkish houses. This was actually designed by That's I don't know how to pronounce properly, and he had this paper, proposed the Turkish houses, and with various features, and basically 4 types according to the position of the holes, and then all sorts of types. We basically can convert all these original rules of Turkish house to the graph grammar representations. You can see, one-to-one correspondence very easy, right? And we just do the first thing, to validate whether our graph grammar idea is feasible, okay? So we did our initial evaluation using our tool called Veggie. Veggie is a tool that supports SGG, parsing and generation in both directions, okay? And so that's also our software tool we developed ourselves. And basically, we input the shape grammar for the Turkish house, the grammar in the previous slide you saw. We input that, and then transform the input to the SGG graph representation, okay? And then transform shape grammar rules also to the SGG rules, and then use the SGG rules to parse and validate new houses, okay? And see whether the new houses belong to the supposedly Turkish houses, okay? So we basically validate 2 Turkish houses, one on top, and that is parsed. That is correct. And the second one we pass, you see this kind of shape doesn't belong to Turkish house because the parsing failed. We use our tool to parse this input floor plan. Basically, it failed. So that means this doesn't belong to the Turkish house. If you go back to look at the Turkish houses, there's no such shape, actually, okay? So this is the first step. We try to prove that our approach works, okay? Then we step into the second part, a little bit more complex, that's actually more useful. So basically, we want to generate and validate Frank Lloyd Wright houses. And I guess that a lot of you know this architect, and you know better than I do, I'm sure. Okay. And his houses are really just the most traditional residential houses. And the floor plan consists of 3 areas: living area called LA, service area SA, and the bedroom area BA. Basically, 3 major areas. And then LA refers to some, terrace, porch, and lavatory, and library, and so on. And there is a bedroom sub-areas that refers to closet and balcony. Some bedrooms have, a closet inside and could have a balcony. Okay, so this is his design, and we also kind of have a hierarchical structure to represent that. You can see that this is only illustration. Okay, it's not by any kind of generation or whatever. Illustration. So 3 areas, and on the individual areas you have different sub areas, and living sub areas you may have living sub areas, and the bedroom sub areas you may have this could be as we said, could be closet or balcony here. So basically that's the tree structure, and in our term we call it tree structure. It's a hierarchical structure is represented as a tree. This looks like a tree, right? And then we actually write the right house grammar rules. Okay, you don't need to go through all this, and this is just an example features we specified among all these rules. I think 25 rules. 25 rules, like this only 4 sample rules that we specify, and living area in the center connects with a bedroom area and a service area. This is a 24. This is how we connect. The service area and the bedroom area is connected to the living area. Okay, so this is just to sample a few rules. Okay, we don't need to go through this. By the way, these rules are manually designed. Okay, we need to write those rules. Okay, and we need to write these rules using our software. We can actually construct these rules, and then we can validate the various right houses. And this is another feature for single-storied houses. And basically, there is a feature that bedroom areas directly connect with living area instead of stairs. There's no stairs because it's a single floor. Okay, and no stairs exist in such houses. So this would be much simpler and without different floors and just one level. So the rules, we have much less rules. So this is our validation results. And we basically used write a book. There is a book consisting of totally how many actually 67 floor plans. Actually, we validated according to different period of time. So you see, our validation shows that our precision is pretty high. That means about 80% of the houses published in that particular book truly belong to right houses according to the rules, the grammars. But why in those 2 periods that less numbers, percentage of precision is lower? Because actually that's what we concluded. Wright was influenced by Japanese and California buildings of modern architecture in those 2 periods. So his houses somehow he designed violated a little bit his own rules. Okay, so some of these houses don't belong to his original design and influenced by Japanese and California architectures. So, and somehow last time, actually a few months ago, I presented this to another architecture school, and one of the professors says, "Oh, actually, I recall that particular issue." I don't know whether it tells you something, because to me this I don't know, and we basically try to find the reasons according to our results, right? And that's how we explain. Yeah. Hopefully it's true. Okay. So then we went further to generate, to do some theoretical generation part so that the user can specify the floor plan and also give constraints as well. So, and we just have some simple sort of concepts to introduce, like a phase. And this is according to the standard kind of graph theory kind of concepts used by the previous architecture designers. And of course, they use computational methods. So like a phase and a dual graph. And let me quickly go through dual graph. I'm sure you probably understand that concept, right? Because this basically one-to-one correspondence with this floor plan, and that's a dual graph. That means every actually phase here is a node, becomes a node. If the two rooms have the neighbor, they connect with each other, there's a link between these two nodes. Okay, so this is called dual graph. There is an existing program that can automatically convert from this to this. Okay, nothing new, and we did not do anything new on this. And then, of course, this is another concept called the properly triangulated planar graph, and also certain properties that we satisfy. Again, this is not our own contribution, okay? And also, again, the previous theory, in order to meet the kind of floor plan features that we have to follow these properties. And here is yet one more concept called rectangular dual graph, and has the following sort of properties. It basically consists of non-overlapping rectangles like this one. This is a very simple example, and each vertex in this G corresponds to a distinct rectangle in here. Each of this corresponds to this, you can see, okay? And there is an edge between them if, they are adjacent. If ij and adjacent, there's a, okay, so this is easy. And then user specification, this is probably too simple for you as an architecture design or architects, that we allow users to provide specifications like this. Node constraint, say, I have one room and one type of room that has so many instances. I have an edge constraint that those two rooms connected for how many times and so on. This is the example, like say A room and two B rooms. There are basically A connect to three B rooms. Okay, like this one. A connect to three B rooms. Okay, so this is the order doesn't matter. Okay, so and also there is only one A. This means only one A. And this second example, A and B, A connects to two B's, and C, there is only one C, and there are two B's. Okay, so anyway, very simple specification, assuming that we allow user to provide us with this simple data. How many rooms you want? How many? Yes. C is connected to A. Yes, that's supposed to be, yeah, correct. So that's supposed to be A, C, and 1. Exactly. Thank you for observing this. This is incomplete. This is just example specifications. Yeah. Oh, I probably should write a complete specification here. Okay, good observation. Thank you. And then we generate graphs according to our input IFC files. You can input this, and then we input our grammar rules. And this is our own graph grammar rules, okay? We input. And then we generate this graph. Like, this is 2 examples, okay? 2 examples we generated. And then we automatically convert them into the so-called triangulated graph. We make them as faces, you see, closed as faces. Each of them is one triangle. It's called a triangulated, properly triangulated planar graph. Planar graph means that it's only in one space, right? There's no overlap. Okay, so this convert to this convert to this. Automatically, we can actually use the algorithm to convert this. Okay, and we did propose the algorithm to convert this. Why we do this? Because only satisfy this PDP graph properties, we are able to convert back to floor plans. That's how we have to do. Okay. And then we allow the user to actually modify the rooms. Say, I want to actually insert a room that's supposed to connect with these 4 rooms. So actually, this is like operating on the graph. Insert a node, okay? And basically insert here, you see, then it becomes here, right? Insert a node here, or delete this D. Delete this D after deletion, this one here. So, as an architect, you may from time to time think that, actually this graph I want to modify. Actually, I want to remove certain nodes. I want to add certain nodes, certain room. And also, another feature is that I want to move a room to the boundary, to the side that has a window. Some rooms in the middle, right? So I want to move to the boundary side so that it could have a window. So that's another feature that we could specify, allow the user to specify. So this is the generated floor plans according to the previous graph. After insertion, the rule, you see there's 3 possibilities, all satisfy the previous graph. And this generation algorithm is adapted to generate floor plans. And generated floor plans could be either similar to the input. Your input, remember, is an IFC file, right? IFC file specifying already existing floor plan. So we assume that you may want to do this. You want to have existing floor plan. Now, please give me all different floor plans that have exactly the same connectivity as my input floor plan. Okay? And the rooms neighboring to each other exactly the same, but different layout. So we just assume that this could be one of the requirements, that usable requirements. And also, but with the same connectivity among the shapes, as I said earlier, that the rooms are still connected in that way, but in terms of layout, they actually are varied. Okay, so this is what we can guarantee. And then the generation process basically is going through this way. That step 1, and we basically generated this directional what's called the path digraph. It's called path digraph, recursively traverse left edges, and so on. And these graphs simply specify that which node is on top of which other node. That means which room is on top of the other room. Okay, that number 1 is on top of 5, for example. Okay, so I'm not going to too much details here, but through this, then we basically can automatically generate the plans like the following. That you see according to these steps, and basically firstly always partition the column first, and then 1 and 2, 5, and so on, and then expanding 5, and then inserting 2 and 4, and so on. And this is kind of steps, and using our kind of we call it rectangle packing algorithm. We adapted that algorithm to actually generate this plans. Okay, And so there's 3 steps. And then user can also specify detailed constraints like plan size. I want the total size to be this, and also aspect ratio. That's what I thought about. I don't know. It should make sense, I think, intuitively, because these rooms look too long. I mean, you probably don't want those kind of rooms, right? So you may want to specify a certain ratio, right? And also room position, for example, on the boundary, having windows. That's what I mentioned earlier. You may want to specify certain rooms, I need to have the window, okay? So that then you see these 2 rooms, according to aspect ratio, we can actually generate these variations. You can see that it doesn't have this long, very long, narrow rooms, right? But the connectivities are exactly the same as this, okay? And also this shows how we actually move a room to the boundary. This is suppose this is an entire floor plan, and this room is in the middle, okay? I want to make this room actually to the boundary, okay? And we simply just moved it there in between these 2 rooms. And assuming that in this case, how do we move it? And we move it between this A and C, move this room, and D stays the same. Basically move this room here. Okay, and this is all, once you specify that I want room I to be on the boundary, so this is done automatically. Okay, the moving itself is done automatically. And of course, I mean, this may not meet your requirement. You may say, oh, actually, I want this room to be here. Okay, and then we have to move it and manually in that case. So what we did is that then we evaluate the generation speed. And, we are doing computer science, so the speed is always an issue. If it takes ages to generate a floor plan, it's not useful, right? So we basically check, with the aspect ratio, without the aspect ratio, and we see how that would affect the speed. If we specify aspect ratio, but we find actually the speed is not quite affected somehow. And also, with the increasing number of rooms, the generation time increases linearly. That's why we say our approach is scalable. It's basically linear. Okay? And generate potential design in less than 5 microseconds for most common floor plans. So it's basically, it doesn't take too much time. And we just use our very ordinary laptop computers, no really powerful computer to do that. It's not from a GPU or from multiprocessor machines, just ordinary PC. So basically, just prove that our approach is scalable and also usable, and the speed is tolerable. And then we, I mentioned earlier, we implemented this SGI, that means shape grammar interpreter, the interface that you can specify and generate. And then some more generated floor plans. As I said earlier that we can generate a lot. Exactly very different floor plans, but meeting exactly the same rules. Okay, so maybe exactly the same connectivity. Okay, or adjacency. Okay, we can generate. So like these are the different results. And finally, these are the processes. We actually show different steps and how we generate and finally produce the 3D model. Okay, and we only realized afterwards to publish in a powerful journal, high-level journal, you have to show this. I don't know why. And then the architecture students say, oh, this is easy. We have software. We just, from here to here is it's very easy, right? But anyway, this probably looks nice. Okay, so that's all for that part. I'm sorry to, rush a little bit fast because I have a few more other slides I want to share with you about other projects. Now, some of you may be interested because they are just quickly run through. Like this is we call edge modeling. This is original US air traffic data that looks chaotic, right? And if there is a flight from here to here, there is a line. You can't see any pattern. So if we can actually bundle the closely related edges together and give a different color, it shows the patterns, right? And basically 4 major routes between east and west and east, right? So this is a so-called edge bundling. We bundle the edges together. This is one technique we do. And this is another result, that application. We show, this is a top journal called the Attribute Transaction on Visualization and Computer Graphics, the citation relationship. If there is a paper, 2008, citing a paper in 1996, there is a link, right? Again, this graph doesn't show anything. So if we bundle the edges, you can clearly see certain patterns. And also from this pattern, we discover that the citation has a kind of a delay, somehow 6 or 7 years between. Okay? So that also shows 6 or 7 years in that particular area is a typical time for the work to be recognized. Okay? So this visualization kind of help people hopefully to discover certain information that you cannot otherwise discover. Okay, I think I will probably skip the demo. This is a demo. It takes probably 2 or 3 minutes. Do you want to take a look? See whether it's too slow. This is an edge bundling demo. I just explain a little bit. You see, we can actually change the so-called tension. That means you bundle how strong you want to bundle, the strength of bundling. You see, there's no strength. That means you don't bundle. And then you increase the strength and until it's very, very strong. So the bundle becomes so strong. Okay? So that you can also zoom in to see the details and no bundle at all, and so on. So that's just to show this, some details, and also we can actually remove the nodes and display the nodes. So far, you see, we can make it black and white. Sometimes black and white is more useful, and also I think show the nodes. These are the airports. And we can hide them if we want. Okay. I think, these are the short edges. Short edges actually are noise. They actually don't contribute to the long edge bundling. So sometimes we need to remove them and show them again. So let me switch to the next application, which is in virtual reality. And in the 3D space, we also have this data, but this is a refugee data set. Refugee, that means move from this world place to another world place, and then there is a link. And in visualization, you see, when you have a directed link, you cannot use arrow. Okay, we don't use arrow. If you use arrow, that means there are a lot of arrows on one end. You don't tell the difference. So instead, we use a color. So, beginning is red and the ending is green. So you can clearly see where it starts and where it ends. So this is why the lines kind of have a green and red, gradually changing from a green to red. That sort of way. And we implement this. You see, this is a no bundle, and this is a bundled edges. Actually, we implemented in the 3D virtual reality environment. And just quickly see. This is too slow, so that's why sometimes I want to skip. This is a sort of a view from inside, and actually you wear the Oculus goggle, and and when you rotate your head, you can see actually the moving of the sphere. We suppose the viewpoint is supposed to be in the center of the sphere. Okay. And let's continue that a few more. That is stock visualization, like positive market and the negative market visualization. Just colorful. And this is a different industry, and on the different industry, the company names. Okay, this is visualization is one of my research area. This is investment in education in the U.S. We actually use the psychology theory called feature integration theory. That means that it says that when people observe something in a very microsecond and nanosecond, you actually suddenly observe the general pattern, and then you look in details. 2-stage. So that's what we try to use that feature to actually use the flower to represent the education investment. Different shapes of a flower to represent different investment from federal government, state government, and private sectors. And then we did the experiment on that. So this is sort of interesting experiment. This is another thing to show the per capita income of 180 countries, also visualized like this. 20 years going this way. If it is becoming black and dark here, that means a fast development. And India, China doing well, and North Korea, you can see. And Ireland did well as well sometime, and the US and Somalia. So this is just an example. Countries and visualization. And also to evaluate the usability, we kind of you apply eye tracking. In psychology department, they use eye tracking. Basically, looks at where you have seen and following your eyes. And this is a logistic visualization for Sydney Airport, and the data moves around. And I skip this, but. Earlier on, I mentioned about the tree visualization, which is a hierarchical data structure. Hierarchical data structure, how do we visualize? You use a graph to visualize hierarchical data structure. So there is a German professor has a collection of all these different tree visualization approaches. So this includes some of our works, and this two, and this one, and some more of our works. And we call cabinet tree, and this is different tree visualization approaches. So, and this is one of them that we visualize the music structure on the cell phone. Can you see the kind of different levels, right? The audio, and then African different languages, and on the languages, genre, and then artist, and then album down here. But, in one screen, you can see several levels, right? And the branches going this way. And but in our cell phone, in one screen, there is only one level, right? So we did experiment on this, comparing with existing approach. We actually we perform much faster, actually less number of touches on the screen for selecting the same music. I skip this and I show this. This is visualizing 500,000 folders and files in one screen. And this is a root directory, and a level 1 directory, level 2 directory, and always change 90 degrees to go into one more directory. And then the directories are color-coded green, and the file types are color-coded warm color. So you can clearly see that there are a lot of this type of files, maybe executable files, right? And interestingly, you can see this area and this area look very similar. Why is that? Two subdirectories look structurally very similar. Even file types are similar. What happens? Can you guess? It's backups. Backups, right? So, assuming that you go to somebody's file system, you want to find where the backup folders. That takes ages. It's very hard to find, right? But if we can display this way, you can immediately recognize. Okay. So these are the some visualizations, and this is a visual analysis of P2P lending market using sort of a fluid dynamic visualization. And I think there is an event visualization that we actually won the top award like this. I skip this. This takes a little bit of time to explain. And there is a video, but I show you some generative art stuff. This is a Tibetan tanka pattern generation and geometrical forms that we automatically generate. Okay, and you know, Tibetan Buddhism, they have this tanka kind of art, their top art, and we also generate moving sand pictures. You know, moving sand pictures, I just saw that in Libre's local gallery. They also have the sand playing for kids to play the sand, because you know the two glasses on both sides and the sand in the middle. You know, you have the liquid inside and the sand can float down, right? So they can form all sorts of interesting patterns. And so this is our computer generated, and modeling the sand effects generates interesting patterns. And this is generating Kandinsky's painting. This is the original Kandinsky composition 8. And this is our program drawn, rendered. And but you say, yeah, why you draw exactly the same thing? Well, the idea is to randomize and parameterize so that we can generate different images of the same style. Okay, so it's just randomize and so generates all sorts of combinations. 1 minute it can generate 1,000 different images, different. They are all different. This is just an interesting experiment, and maybe for graphic design. And this is another Kandinsky painting called Black and Violet. Another one called On White 2. These are all computer generated, and several circles. This is called a soft hard. We can even combine different paintings together, have different elements mixed, and then based on that, we can actually generate Kandinsky fonts. That's what I recently did. So I sent Ding Okamura, your university is in this fonts. Okay, and this is 26 letter, uppercase letter and lowercase letter, and so on. You can, because this is generated, it's a vectorized, and you can change color, you can change size, you can change the rotation, anything you can change. Okay, so that is hopefully useful, and different sizes and different aspect ratio as well, and metallic type, and this is what I sent you, and hopefully it looks interesting. And also the Pollock. Do you know American artist called Pollock? Basically, it's a dripping style. Pour the paints on the canvas. So this is the original painting, and this is our computer generated. And can you see the difference? This is original. This is our generated. Okay, and this is the original Pollock number 8. Very, very decorative. And this is our generated. Okay. So this is Miro Poetis in that series called Constellation Super Surrealism style. And this is our computer generated with different background colors. And this is another computer generated based on this, Constellations in Love with a Woman. That is the title of his painting. Okay. Then this is our recent work on the Picasso Cubism. This is the original painting, the girl with a mandolin, and our generated, not that good, right? But then we improved that. That's how we did. I will make it really a Cubism style, a half face facing this way, half facing this way, right? So if you input your portrait, we can convert it to this way if you like it. Okay. So finally, we did a little bit work on the Chinese ink paintings. We tried to look at the blank space, whether they are meaningful. Actually, they are meaningful. And also we use eye tracking. And then we computed the complexity of his painting, like this one, and complexity of this master artist, and we calculated the complexity. The complexity in the sense that at the end, we want to be able to quantify the beauty, or we call aesthetics of a painting. This is a very challenging task. And you compare two paintings, one is more beautiful than the other. It's not very subjective. But from our point of view, that we may be able to quantify, measure. So complexity is one of the measurements that we are doing. Okay. So sorry to take you a long time. That's all for now. Thank you.